Thank you. Okay, thanks everyone for sticking around. My name is Chong Tao. I'm a design engineer at Panametrics. I've been working for Panametrics about 11 years. And my work mostly around the algorithm design for the specific Flare.IQ, which Ray and Victor talked about. The three parts about Flare.IQ, right? It's basically a system or platform, but it contains three major features, which is digital verification we just talked about, and the other two pieces are flare control, right? Mostly around the MAC rules. You guys probably familiar about that. And then also we had a new feature recently about emission monitoring. Whether that's basically it's based on the process conditions, you can predict the combustion efficiency out of the flare, and then also calculate the emissions of CO2 or CO2 equivalents. That's this talk is about flare control and emission monitoring. Small? Which one is small?
Just spacebar.
Which one is small? The other way. Okay, sorry, I got it the wrong way. So I'll start with the Flare.IQ system. Okay, I'll talk briefly about the hardware, software, and then of course deep dive into flare control, the algorithm, how it works, and then flare combustion efficiency in details. So as I mentioned, flare control is basically we call it box. Hardware mainly contains power supply, right? With a redundancy, and then Ethernet switch, and then DPUs. DPU basically just industrial computer operate on Nexus operation system, and both DPUs and power supply has redundancy just for reliability. And one system is hardware, right? One system can power up to 3 flares. So basically with one box, you can control up to 3 flares. In terms of software, it's basically one piece of software, and it has 3 features, 3 main features. One is digital verification we just talked about. The other 2 will be flare control, and we call it PEMS. Basically, it's just combustion efficiency and CO2 emission monitoring. Of course, depend on which license you buy, you can have those features. So for flare control, you see this just minutes ago. For a typical flare system, right? You have a DCX controls the for the steam or air assist, or you have also supplemental fuel gas, and then of course you also have metering for those steam or fuel or flare gas, and for also especially in the US, it's required to measure the BTU content or gas analyzer for the flare gas. Of course, all this is controlled by DCS. Flare.IQ is just another, we call it box, connect to DCS via Modbus TCP or Ethernet protocol. So what Flare.IQ does is based on the process conditions or the feedback from all those meters, you will calculate the set point for fuel or steam or air, right? So the flare control is designed also. It's designed around or based on the MAC rule, right? We talked about. I guess you guys probably familiar with basically the requirements. You need to have enough assist gas to prevent black smoke, but also not too much of those assist gas. So, or at least you need to maintain the heating value in the combustion zone about 270 BTU per scarf. Also, there will be fluid exit velocity requirement less than 400 feet per second, or actually further limited by the BTU content. If your BTU content is say less than like 300 or 400 BTU, the exit velocity is further limited. So all these requirements can be met with the Flare.IQ control. So of course, the reason for that is pretty obvious, right? For example, if you don't have enough of a gas or enough steam or air, then you might see a black smoke, which basically is a no-no for flare operation. And then on the opposite, on the other extreme is you have too much steam, so for example, then you can almost put out the flame and the combustion is actually terrible. So it basically didn't combust much and then just release all the toxic chemicals to the air. That's of course another no-no. That's why you know, especially after TCE studies, EPA said, oh, we need to have this mechanism rule, right? So the way we design Flare.IQ, it's based on the sound speed measurement. That's the key sort of technology we developed. It's based on the sound speed. We can measure the vent gas molecular weight. And the way to do it is actually, I would say it's pretty well known, but not very easy to carry out. It's there's we call it a value state equation, right? Basically, it's just the relationship between the gas sound speed versus the molecular weight, and of course, at the temperature, and there's also like a pressure term in there. It's valued in there. But anyway, you can relate or you can calculate the molecular weight based on sound speed measurement using this so-called value equation. And then, of course, it's a illiterate process or regression. So basically, you have a sound speed, you guess a molecular weight, and then calculate the sound speed. So if it matches, if not, then change your molecular weight, calculate again. So until it sort of converges, that's how you can calculate the molecular weight from sound speed. And that's basically the key methodology for all this control. It's based on this method. Of course, there are some other ways to sort of calculate the molecular from sound speed. Say like empirically, basically say for example, if you assume all the gas are ideal gas, you can calculate the sound speed molecular from sound speed very easily by just a very simple ideal gas equation. You can calculate it, but of course your error will be much bigger. And our method has shown, right, all this gas range from pretty much hydrogen, right, go all the way up to molecular up to 120. That's C6 or 8. Right? It's even about C6 or C8. So basically, in the whole range, the error is between 2%. It's actually 1.8 on average from the sound speed to calculate molecular weight. You can get very accurate results. And then, of course, if you know molecular weight, right, you can do a lot of things. One is you can derive the helium value from the molecular weight. And this is just one example showing, say, helium value derived from our method with mass spec measurements. Overall, this probably 3 days of data, right? 2-3 days of data. Overall, it's pretty good, like between 3 to 5%, depending on the gas and conditions.
I just thought hydrogen had challenges, but it looked like your middle, like around 700 BTU at
Yeah, that's actually this is raw data. I don't want to sort of manipulate it. Okay, there are few, as of course you're right. There are few sort of, if you look at the data in detail, there's some discrepancies. So for example, right, there's some like periodic sort of drop from the mass spec. I mean, this data is from a customer, right? Customer like, who actually using Flare.IQ, and they also have a mass spec measurement. The mass spec, say for example, it has like every once like 24 hours. I think there will be a drop. But I talked to the guys that said, oh, it could be because of sort of calibration. It could do calibration mode because the mass spec has 2 channels. Usually provide 2 channels, but they only take 1 channel reading. So when it goes into calibration, it basically the reading goes to 0, right? That's those jobs. But also they are here, right? We talked about it, but unfortunately, the operators don't know exactly what's going on over there. But of course, it shows up as an error here. But when I say 3 to 5%, we actually remove this section because we cannot account like what's happening for the process. And the reason we took it out is because we can account it, and the operator don't know exactly what's happening. No, but that's, I don't think that's as an sort of I won't say it's cheating, right? Because it works. Okay, it's just at that point. No, it's not hydrogen. Okay, we know actually the whole process, it has about 70% hydrogen. The whole process, right? It's fine. That's not the issue. Okay, but there are periods. I mean, I can, of course, I chose to plot this one because this is a very long run. It's a few days data, continuous, and then of course this specific period, it's because operator don't know exactly what's happening.
Yeah, and basically we try to reconcile with the operator. We have no good explanation either from their side or our side. So that's the outlier we took out for now, and until we have a good explanation of what's going on there. Yeah.
That's develops.
Yeah, but it's you will see, right? This just okay. We have Flare.IQ installed more than a few dozen, like almost probably 50 or even more than 50 installations. Okay, it's very reliable. Okay, this is just one example I'm showing you, and I will show you. Say for example, this is another example, right? This is it's different refinery, right? A different customer. They have a GC, right? You will see, right? The comparison between sound speed measurement or Flare.IQ versus GC. GC is the black one. You can see overall, right? When there's no flaring event, it's matching pretty well within a few percent. Of course, we all know GC has, so for this case, has 14 minutes response time. Okay, and this is small flaring events. So it's last only 10 minutes or so, and GC completely missing. Actually, Flare.IQ has a response for 6 seconds. Okay, it's almost instantaneous. So that's why you can see Flare.IQ measurement. It's 14 minutes ahead of GC. Okay, and then there are 2 another small events. Of course, you will see a slight difference between, say, the sound speed with GC, because if you know how GC works, right? GC has a sample system, a long sample system, to have a sample sort of prep system, right? All those will act as sort of a filter, right? A smoothing filter, right? That's why you see that the second peak, especially, you see that a slightly smaller peak but wider peak, right? It's basically you feel if you go through this like sort of a high narrow peak through a slow filter, it's gonna smooth out. Right? That's the difference. But the main takeaway is that we all know, especially the control engineer knows, GC has latency, right? 10 minutes, 8 minutes, 14 minutes, whatever, depends on your system. But especially like according to the regulation, right? You cannot have more than 5 minutes of smoke in 2 hours period. But if your GC it's like 10 minutes or 15 minutes slow in response, then you already have 15 minutes smoking events, right? That's basically you cannot win unless people just watching it 24/7, whatever. But if you use Flare.IQ, response time is 6 seconds. Okay, then you don't need a sort of GC to tell you, yeah, we have flare event. You need to open your steam to put out the smoke. So this is just showing you the whole diagram showing you how Flare.IQ works. But as I mentioned, right, the key is from the ultrasonic flow meter. You have a pressure, temperature, and sound speed. Right? You can estimate the molecular weights, and then of course, flow meter also provide flow, right? From the molecular weight, you can calculate the heating value, and then of course, based on all those flows, right? Your fuel flow, steam, and then flare flow, you can calculate the heating value of the combustion zone, right? And then of course, based on the heating value in the combustion zone calculation, or your limit, whatever is that 270 or 300, whatever number you set, you can calculate how much fuel you need, right, to sacrifice the requirements. And then of course, based on molecular weight and the flow, you can also calculate the steam required to prevent black smoke. Right? And then, of course, based on the calculated fuel or steam demand, you can send this back to DCS. So basically, you provide the set point to DCS, and then DCS will respond to the set points. That's how you can automate flow control, but using Flare.IQ, right? And then you mentioned GC or mass spec. Yes, GC or mass spec. It's in most cases it's optional, but it's better to have because especially if you have a lot of hydrogen, for example, right? Hydrogen burns differently than everything else. You all know that. And like say steam calculation, it can affect the steam calculation, right? And also because of those 12 rules, I'll show you guys know, but you can use 12 BTU per scarf for hydrogen instead of 270 BTU per scarf. So basically, you can use less fuel if you're burning a lot of hydrogen. Then, of course, if you measure that, you can take the credit and use less fuel. And then also, like say, nitrogen or other non-combustible gas. If you have those in your, especially a large amount or larger variation of those, you can have more accurate measurements if you have GC or mass spec. But otherwise, this Flare.IQ can operate without GC or other gas analyzer. Purely based on the sound speed and the flows, you can automate the control without an issue. Right? We have Flare.IQs outside US, like in Middle East or Europe, in Asia. They don't have GC, right? They only sample their gas every once a week or a month, whatever, right? They don't have online GC. They can still utilize Flare.IQ to automate the flare control very well.
So Jeff, Paul, basically Flare.IQ can be self-sufficient. The only thing is when it comes to reporting the NHV value, based on the EPA, it's pretty much they take the GC or mass spec or calorimeter. Those are three. I mean, as a manufacturer of Flare.IQ, normally historically we don't push this technology to be accepted by TCUQ or EPA or wherever. However, and based on our initial data from the customers, we can be self-sufficient, and we can also be used as a reporting tool. It just not have been blessed by regulators there. So that's the real deal here. That's what the Chong is trying to say.
Yes, but of course in US we know because of the MAC rules, every refinery is required to have GC or mass spec or calorimeter, right? But yeah, you're just they mentioned you can use Flare.IQ for control, but you can use say those GC or mass spec or whatever for reporting, right? But if you look at the live data, right? The values from, or the heating values especially, right? From GC or mass spec versus Flare.IQ, it's comparable. When I say 3 to 5%, that's real data. Okay, that's you can look not just one flare, right? There's several flares. I mean, 50 or so. But you can know it's within that percentage, right? And actually, we have a customer. They are trying to say replace the GC data with Flare.IQ data, especially when GC is down. I know I worked with a couple of customers. They have an issue with GC because GC requires daily calibration, but a lot of times when the calibration only covers say light hydrocarbons, say for example methane, but they have a lot of say butane or propane, which is sometimes can go out of their calibration range. That can cause an issue with GC. Right? GC did say, for example, if the GC is calibrated up to say 50% of propane, and their propane gas is say 80%, it will stop at almost 50%. You cannot go above their calibration point. And that the extra 30% will be counted as most of the time is moisture. Right? That's how GC works, okay? And in that case, your GC are so wrong, right? It's off by the.
But when you showed the slide on when the ladder logic got backed up because the GC, taking samples every 7 to 15 minutes. You're still to be able to use the Flare.IQ model for process control. You're still taking the GC input. You're just inputting data and using a predictive model to smooth out the curve, aren't you?
No.
You're just
okay. This data, right? As I just mentioned, this data has nothing to do. Like say the heating value or the control has nothing to do with GC, okay? It can operate without GC at all.
So what are you using for the input to come up with the heating value?
Sound speed.
Just
sound speed. That's the magic, okay? And that magic is not coming out of nowhere. It's well known. It's called Wilder's equation. It's from 1940s, 1960 something, okay? Those are well known. Those are hard science, okay? The equations to describe it. And that's our pattern actually for over almost 20 years now. Mass ultrasonic flow meter measure the volumetric flow. But how do you get mass flow from volumetric flow? You need the density, right, for the gas. Density is basically molecular weight. Mass and molecular weight is just a different term for density for gas. So you need the density. So the way we come up with the density is from sound speed. You can calculate molecular weight or the density. That's the beauty of this one. Is you don't need extra stuff. You already have it because you have an ultrasonic flow meter measure flow. all you need is pressure temperature, right?
But using the sound speed to calculate, to estimate heating value or molecular weight, that's where I thought hydrogen plays tricks with that equation.
Yes, that's why I said there's a difference between.
If it's just alkanes or.
Yeah. Then also, if you say, for example, if your hydrogen is only say 30% plus minus 5, right? Then I would say I'll put 30% there. I will take 5% plus.
Of a variable hydrogen stream.
Yes.
Probably wouldn't use this.
Or I would say this, I get your question there. Basically, for Flare.IQ to operate, we don't have to rely on the GC input to optimize there. However, what you said is that
it's accuracy.
Yeah.
It's accuracy.
Yeah. So for reporting purposes, yes, GC, you need GC for that. And then if you within the 15 minutes window or whatever response time of the GC, if you have a lot of variation in terms of hydrogen content, right? In terms of hydrogen, you just mentioned. So one of the downside is for Flare.IQ is we don't get the details of the content. You are assuming certain percentage of hydrogen over that period of time, right? You might not be able to utilize the full hydrogen knowing the content that then give you a higher HV value of that. That's the part you lost. But in terms of hydrogen changing over 7 to 10 minutes, I mean, unless you have a different view, I don't see that changing drastically over time. I mean, that quickly there, right? So maybe you have a better example you can share.
I think, that's like an example of upside conditions. And when I was trying to sell one of your systems to somebody out on the West Coast,
yeah,
who needed it to resolve some compliance issues.
Yeah.
Maybe you'll have more success now that they're no longer, now that they've changed company names. But I think this system is good for that type of atmosphere where there's a lot of public scrutiny. Because you can help smooth out the curves and avoid the slowness and ladder logic of waiting for GC cycles to catch up. And over time, for accuracy, numbers, pan out for annual reporting, but who cares when you're dealing with people?
That's actually
black smoke or over steaming.
Yeah, that's exactly the point. It's
minutes.
Yeah, especially you have a lot of upset conditions, right? GC is just
not a lot.
Even if you have GC, some of them I don't know.
And I think
outside US, they don't have GC, and then all the upset conditions just all manual. And most of the time, you know how it operates. It's just somebody set their steam there, and they probably never come. Maybe 2-3 days later, they change it again. Right? That's how it works. But the beauty of this is it's almost instantaneous, right? But of course, 6 seconds. 6 seconds mainly because of the communication between DCS and Flare.IQ. The Flare.IQ calculation itself takes less than half second or 1 second. It's very
to iterate the moment.
Yeah, it just take seconds, 1 second or less. But
so
the
then
communication,
the variability of the amount of nitrogen and water would probably critical factors that create problems.
Yes, but those are, I call it accuracy issue, not necessarily sort of a control from control aspect. Those are usually can take care by this method. So, for example, if your molecular weight goes from say 10, which a lot of hydrogen, goes to like say 40 or 30. Then you say your steam ratio need to increase dramatically, right? Of course, if you have like nitrogen change 5% during that upset condition, you have 5% or 3% error in terms of steam calculation or heating value calculation. So what? Extra 3% extra error, but you are still you're doing most of the work, which basically you prevent black smoke and your heating value is, instead of set at 270, you set a buffer like the 10% buffer, right? And then it's all covered.
Jeff, I mean, long story short, it can be a limitation, right? Just like any other technology, certain comes with a certain limitation. I mean, if we think about the source of the nitrogen, I mean, a lot of those can be from, you know, the injected, I mean, for the keep the positive pressure point B, right? So those, they normally don't change, but that all.
When we're dealing with maintenance, startup, and shutdown, you have dramatic changes.
Yeah. Those conditions, operators usually know they can bypass or you can override Flare.IQ in that case, especially if they're brushing their systems. Yes.
That's a fair comment. I mean, there's no perfect technology out there, but yeah, that's the one thing we should keep in mind.
Okay. So the second part is the flare combustion efficiency monitoring. It's basically it's very similar problem, but a different aspect, right? So first part is control, right? Second part is, yeah, EPA says, okay, let's do this control so we can have 96.5% combustion efficiency, right? And of course, yeah, that's mostly it's true, right? That's based on most of the data, but in reality, it can be fairly different. So also they mentioned how the operators, how you operate the flares can have a very large impact on, what the actual combustion efficiency, right? It can be, 50 or 30%, it can be 98%. So it depends on how you operate it. And of course, we always want to strive for this 98+%. But the problem with that is, okay, how do I know my flare is high combustion efficiency? Right? We won't know unless we measure or we call it monitoring. And so what we come up with, we call a Panametrics model. So what this model is, it's originally basically based on all those tests. A chunk of it's TCEQ, right? Then there are a lot of studies, Marathon, Detroit, and Texas City back in 2010, 2009. And then there are some other operation about flare combustion efficiency studies. And then, of course, based on those studies, and then a lot of CFD studies as well, right? You can find out what affecting combustion efficiency for flares. Right? Major parameters or factor is heating environment and combustion zone. We all know that, and that's also actually what the EPA MACT regulation come up to 70. That's none on here, but some other factors like wind, exit velocity, right? Gas composition in terms of, say, pi bond or the olefins or unsaturated hydrocarbons, carbon hydrogen ratio, right? And then also pipe diameter, hydrogen, for example, right? And then non-combustible, like mostly nitrogen. All those can have effect on your combustion efficiency. And then, of course, if you have a cyst gas, then a cyst gas also is part of combustion efficiency. But so basically, what we come up with, based on all those tests and safety studies, we come up with a model. Basically, we call it Panametrics model. So, for example, right, you can have a heating value. What the heating value effect? If you simplify it, right, it will be something similar to this, right? Then how the combustion efficiency can be affected by heating value. And then, for example, the wind effect. Wind effect, it's U. It's a crosswind. V. It's exit velocity. UV effect. And of course, a lot of times it's not one-dimensional, right? We know that it's more complicated than just a few factors. Yeah, plugging those. No, it's it's a combination of a lot of things. So for example, UV effect. It's not just UV. It's a heating volume. It's a diameter. All those can affect this UV effect. If you plot just one case, right? One case, say this UV effect for like 24-inch diameter pipe and heating value of 45.6 megajoule, roughly like 1,000 something BTU per scuff. You get very complicated sort of correction of those UV effect, and that's what we are dealing with, right? You get a complicated parametrics model which take care of all those inputs. Let me see. All the inputs are basically, as I just mentioned, all the possible parameters, right? But fortunately, right, almost all of them, I won't say all of them, but almost all of them, especially the key parameters, can be achieved with flow meter, right? With a wind measurement anemometer, very simple one, right? That's part of sort of extra device you will need for flare combustion efficiency calculation. And the key concept is, again, right, from sound speed, pressure, temperature, you can calculate molecular, you can calculate heating value, and from other input, say for example, right, wind measurement, you can measure the wind. If you have GC, for example, right, you can measure all those as input, right? And then of course, if you have with non-assist, then there will be no steam or air. But if it's assist the system, you will have those as well as input. So based on all those inputs, and based on the, of course, we have different model for different CE model for different systems. Say, for example, upstream non-assist flare system obviously works different than assist flare. Steam assist works different than air assist. But we have all the, sort of three different models where with this inputs you can predict or calculate or whatever the combustion efficiency, right? Based on real process data conditions, not just say assumed 96.5 or designed combustion efficiency of 98. Right, that's people are using, but in reality, we all know that it can be quite different. And this Flare.IQ provide a live measurement or calculation of this combustion efficiency based on flare operation conditions. And I want to show, this just the like analytics based on the model with testing data, right? There's basically split out all the test data into sections. One is high heating value region, where say the heating value in the combustion zone greater than 300. The error, of course, it's much tighter, right? On average, it's about 1.something% compared to test data. Right? In the low heating value region, it's much larger for a couple of reasons. One reason is actually in this region, the measurement itself, I can tell you it's not very accurate. You know that it's usually we are talking about 15–20% for the measurement at all, in this region. But also, of course, this model because the combustion efficiency is so sensitive in this region, so sensitive to the variations of, say, like wind or the heating value measurement or the gas composition, then that also contribute to the error. But the good part about this is, especially if you are really controlling your flare, you're not operating in this region. I won't say forever, but most likely you're not operating in this region. So yeah, it's high error, but really it's not the region we're interested. We're interested in this region. So.
Telling you about 2 more minutes.
I'll be on time. Yeah. Okay. So so I'll finish with the Flare.IQ calculation result versus camera result. Okay, this is done for upstream, actually 2 upstream flares. Okay, so the black line it's a measurement from a camera. It's I'm not sure if you guys are familiar. There's a Providence Photonics. They have a versus Mantis, yeah, Mantis camera. To measure it during 6 days, right? A couple hours a day to measure it 6 days. Measure the combustion efficiency for upstream flares, and then we have Flare.IQ calculation. There's a red and then purplish. The reason black only has one, actually it's 2 flare sort of very close to each other. It's called HPM LP flares. Camera basically cannot separate those 2, just measure, sort of combine the results. And then of course Flare.IQ, because you have 2 systems, so you can separate them because they have nothing to do with each other. So overall, I would say it's pretty good in terms of for the majority of the case, right? There's some cases where you will see large discrepancies. Say, for example, first day you see large discrepancy because in that day it was very windy, very windy. It's like 30 miles wind, 20 something 30 miles wind. I won't say Flare.IQ is more accurate than camera, but the fact is it's very difficult for camera to image at a certain angle when the wind is that strong. So and then for the rest of the few days, they are in pretty good agreement. And also another takeaway is this upstream flare, and when most of the upstream flare reporting based on the design combustion efficiency of 98%. Okay, that's here. So when you report your flare combustion efficiency, it's 98%. That's a design combustion efficiency for these flares. So those are the number they use, but of course your measured data. It's I believe the average measurement for camera is close to 98.7-ish. Flare.IQ is close to 99.1.2-ish. So there's a huge difference between 98 versus 99, right? That's 50% difference. It's not 1%, it's 50% difference in terms of emission reporting. So that's why you wanna monitoring live instead of using a designed or fixed number. Same as emission factors is very similar fashion, but that's why now this sort of still kind of like very early in terms of technology for regulations, but this is what we probably moving forward to, right? Live monitoring instead of a fixed number. So yeah, that's what I have. Thank you.
Thank you. Good time.
Yeah.